Very good morning, students. Welcome to Purnachandra Higher Secondary School. Okay, so in the previous class, we are discussing about the Ampere's law. Okay, the application of Ampere's law is a very important, which I have discussed in the previous video lecture. Clear? In this class, we are discussing a very important topic. Okay, that is, we have to find out what is the force on a charged particle in a uniform magnetic field. Okay, so what do we have to find out? Now we have to find out the expression of force when a charged particle is moving with a velocity, with some velocity in a uniform magnetic field. Clear? So we are discussing about that one. So for that, let us have a figure. So look at the figure very carefully. Okay, so what the figure says? There is, let I will assume a positive charge plus q. Okay, so I have taken a positive charge plus q, which is moving with a velocity v, in this direction. Clear all of you? That means the velocity makes an angle theta with the y-axis. Very simple. Clear all of you? Okay, so now, so the plus q charge is moving with the velocity in this direction. That means this v component or this velocity, listen very carefully, this v component or this velocity component can be resolved or splitted into the horizontal component and the vertical component. Very simple. So it is splitted into v cos theta and v sin theta, because the component which is attached with this angle theta, I will denote it as v cos theta, and the other component I will make it as v sin theta. Okay, and the direction of magnetic field is along which direction? Is along y direction. That is, this is my direction of your magnetic field B, along y direction. Clear? So that means, is a very important point. So our aim to find out what is the force applied on this positive charge. Okay, that is our aim. So what we have assumed? We have assumed that a positive charge plus q moving with a velocity v in this direction. So this velocity is resolved into two components. One is v cos theta, another one is v sin theta. Clear? And as v cos theta component is along the magnetic field, that's why this component has nothing work, okay, to generate the force. Very simple, because it is along the direction of the magnetic field. That's why which component we will take, or which component the force will depend upon. The force applied on the positive charge will depend upon only this component, that is v sin theta. Clear? So that means here I can write these things. The force applied on this charge plus q is proportional to the amount of charge. Yes, proportional to the amount of charge, because the amount of charge, we know that in the previous discussion. Okay, the magnitude of the force will depend upon the charge. Okay, now the force also depend upon or proportional to the component v sin theta. Clear? And it will not, the force will not depend upon the v cos theta, because both magnetic field and v cos theta component is in the same direction. That's why it has no effect on generating the force, on production of the force. Clear? So v directly proportional to the charge, v again directly proportional to the v sin theta component. Okay, and again the force is directly proportional to the amount of or the magnetic field. Clear? Okay, so that means if I will combine these three, if I will combine these equation number 1, equation number 2 and equation number 3, so what I will get? I can write F is proportional to Q V B sin theta. Clear? So if I will combine these two, I can write Q is equal to F is equal to Q V B sin theta. Very simple. Clear? Okay, so these have depend upon these things. If I combine these three, that is proportional to Q V B sin theta. Okay, or I can directly also write down the F is your nothing but that is q VB sin theta. Very simple. Okay, and that implies it can also be written in this manner, that is q whole into, look at very carefully, so q whole into VB sin theta. B is also a vector quantity, B is also a vector quantity, and we know that AB sin theta is nothing, if A is a vector, B is a vector, so AB sin theta gives me A vector cross product B vector. From Husserl point of view, we know that one. Similarly, VB sin theta I can write as V cross product with B vector. Clear all of you? So that is the expression. Remember, that is this is my magnitude expression or scalar representation of the amount of the force, and this is my vector representation of the force. Okay, force applied on the charge plus q, which is moving with the velocity v in a uniform magnetic field B. Understood all of you? Clear? So remember, these force, whatever applied on the charge particle, this plus q in the magnetic field, this force is called magnetic Lorentz force. Again I will repeat, the force applied on a moving charge particle in a uniform magnetic field. Clear? So that force is nothing but your magnetic Lorentz force. So as it is in magnetic, so I can denote this F as Fm q whole into B cross B. So do not confuse, this M is only for the magnetic field. Clear? So this is the Lorentz force. This expression is nothing but what is called the Lorentz magnetic force. Clear all of you? Now this is the force on a charge particle in a uniform magnetic field. That is called your Lorentz magnetic force. That is the value becomes F is equal to Q1 into V cross B. Clear? Okay. So now next, from this expression we can get a very interesting expression. Look at very carefully. Okay, so what we will get? Now we will get that F is equal to Q V B sin theta. This much we will get. Now let us apply three cases. Suppose for the first case, listen very carefully. For the first case, if theta is equal to 0 degree or 180 degree, if I will take theta is equal to 0 degree or 180 degree, what does it mean? What is the significance of it? The significance of this 0 degree or 180 degree means the angle between the velocity and the magnetic field. Again I will repeat, the angle between the velocity and the magnetic fields becomes 0 degree or 180 degree. That means they are parallel with each other. Very simple. They are parallel with each other. Okay. So that means if the charge particle is parallel with or moving parallel with the magnetic field direction, okay, so then the angle between V and B is either 0 degree or 180 degree. Clear all of you? Okay. So now if they are parallel, then I can write F is equal to Q V B sin 0 degree, or we can write Q V B sin 180 degree. And in both the cases we know that sin 0 degree is nothing but your 0, that is equal to 0. That means from this we can conclude that if a charge particle is moving parallel with the magnetic field or is moving in the same direction with the magnetic field, then no force is applied on that charge particle. Understood all of you? Clear? So this is my case number 1. Okay, now come to the case number 2. So what happens in the case number 2? Suppose I just want to take, suppose V is equal to 0. Suppose I will take V is equal to 0. Okay. So if look at here, if V is equal to 0, what does mean? What do you mean by V is equal to 0? V is equal to 0 means that the charge particle will not move in the magnetic field. Clear? The charge particle remains constant in the magnetic field. So if the charge, then we can write what is the value of F. So simply that is q v b sin theta. So if V is equal to 0, then F is again 0. Okay? So that means if the charge particle is not moving in a magnetic field, or the charge particle is at rest in the magnetic field, then also there is no force is applied on that charge particle. Understood all of you? This is the case number 2. Okay. Now come to the case number 3. What about the case number 3? So if I will take, if suppose theta is equal to, I will take 90 degree. Okay. So if theta is equal to 90 degree, then what is the value of F? Now F is q v b sin 90 degree. So that means that is q v b, which I will have the maximum value of the force. Okay. So that means it's a very simple conclusion I can take it from here, that if a charge particle is entering into a magnetic field with perpendicular direction, look at here. This is the direction of magnetic field, and the charge particle is entering into it with a velocity v. This is the charge particle. This is the magnetic field direction, and the angle between them is 90 degree. Then what happens? The charge particle will entering into the magnetic field with greater force, or maximum force. And what is the amount? What is the value of that force? The value of that force is nothing but your q v b. That is the product of the magnitude of charge, the magnitude of velocity, and the magnitude of magnetic field intensity or magnetic field. Clear all of you? So these are the important 3 conclusions I can take it from this section. Understood all of you? Okay. So now we are next. Suppose. So here we can also define. So F is equal to what I will get, that is q v b sin theta. So that means from this I can write B is equal to how much? Now F divided by q v sin theta. Understood all of you? Look at this is a very important one. And this B is nothing but magnetic field intensity. What is B? Magnetic field strength or magnetic field induction. Okay, magnetic field strength. Also we can define the magnetic field strength from this expression. How we can define? Look at very carefully. So for this, what I can take, let the Q is equal to 1 coulomb, V is equal to 1 meter per second, and theta is equal to 90 degree. Very simple. Look at very carefully. Okay. So what I will assume? Now let a charge having or a unity charge or having charge having unit value moving with a velocity 1 meter per second, that means moving with a unit velocity with entering the magnetic field perpendicularly. Okay, again I will repeat the sentence very carefully. If a unit charge, unit magnitude charge with a unit velocity entering the magnetic field perpendicularly, okay, entering the magnetic field and perpendicularly, then the magnetic field strength is nothing but the force applied on that charge particle. The magnetic field strength is nothing but the magnetic force applied on that charge particle. So that means the magnetic field strength can be defined as the amount of magnetic force applied on a charge particle having magnitude 1 coulomb, moving with a velocity 1 meter per second, entering into the field perpendicularly. Understood all of you? This is the this is how we can define the magnetic field strength using this expression. Again I will repeat, the magnetic field strength is nothing but the force applied on the unit charge particle which is moving with a unit velocity entering the magnetic field with 90 degree or perpendicularly. Understood? Okay. So what is the SI unit of magnetic field strength? The SI unit of magnetic field strength is your Tesla, denoted as capital T. Listen very carefully. Understood all of you? Okay. So this is how we can define the magnetic field strength from this magnetic Lorentz force. Okay. So now with this we have completed what is the force on a charged particle which is moving in a uniform magnetic field. With this concept, now let us move into another concept, that is, again we have to find out what is the amount of force on a current carrying conductor placed in a uniform magnetic field. Uniform magnetic field. So with this concept, now we are going to another section, important section, that is, again we have to find out what is the force applied on a current carrying conductor. First of all, the important point is the conductor should be a current carrying conductor, and number two, it is present in a uniform magnetic field. So let us draw a very simple figure. Suppose this is my uniform magnetic field B. Look at it very carefully. And in this uniform magnetic field B, I will place a conductor. So this is a conductor. Okay. So this conductor, look at it very carefully. This conductor having area, suppose I will take it as A. The length of the conductor I will take it as L. Clear? I will take it as L. Okay. And this conductor is placed in a uniform magnetic field having N or with an angle theta. Clear all of you? And this conductor carries a current I. Clear? This conductor carries a current I. Very simple. Okay. So now again I will repeat what we will assume. Now we are taking a, you look at it, these are the magnetic field lines, these are parallel with each other. So that's why this is a uniform magnetic field. In this uniform magnetic field we are placing a conductor. Which type of conductor? Current carrying conductor. The conductor carries a current I which makes an angle theta with the magnetic field B. The conductor is having an area A and the length of the conductor I will take it as L. Clear? So now our aim to find out in this condition what is the force, what is the amount of force applied on this conductor. Very simple. Okay. So the area of the conductor is A. The length of the conductor is L. Okay. The current carries, the amount of current carries, okay, in this conductor, let us take it as I. The current carries in this conductor, let us take it as I. Very simple. Clear? Okay. So now to derive this expression of force, we are assuming that N, look at it very carefully, N, small n, is the number of free electrons. Look at it very carefully. N is the number of free electrons per unit volume of the conductor. So we are assuming that, now let N be the number of free electrons per unit volume of the conductor. Very simple. Okay. So now if N is the number of free electrons per unit volume, then what is the total number of electrons? So the total number of electrons, total number of electrons. How much? This is number of electrons per unit volume. That means if I will multiply with this m with the volume of this conductor, then I will get the total number of conductor very easily. So what is the number of electrons per unit volume? The m into what is the volume of the conductor? The volume means the area of the conductor is A and the length of the conductor is L. So this is nothing but the total number of electrons. Okay, so that is equal to A and L. Clear? This part is over. Now, if this is my total number of electrons, what is the total number of charge? Let us find out. So the total charge. So total charge, suppose I will take it as Q. So total charge on this conductor is equal to the number of electrons into charge of electron. Very simple. So number of electrons is your A and L, and what is the charge of electron? E. Very simple. Okay. So total number of charge, the total charge of this conductor becomes A and L E. That is A and L is your total number of conductor. E is the charge of one electron. If I multiply these two, I will get a total charge. Clear? Okay. So now after getting this, now we can apply the Lorentz force. Simple. Okay. So applying the Lorentz force, we can write applying Lorentz force. Okay. So applying Lorentz force. Lorentz magnetic force. What I can write? Now Fm is equal to Q whole into V cross B. Okay, Q whole into V cross B. So now look at here. Look at here. So that implies. So in place of Q, I can put this value. So F M is equal to A N L E whole into, that is V cross B. Okay, so that is equal to, now what I can take. Okay, so let us take. So now another very important concept here. The velocity means velocity of what? The velocity of free electrons. And from the current electricity chapter, which we have discussed in the previous video lectures, we know that in this condition, what is the velocity called? The velocity is called the drift velocity. That's why we can call it as Vd. Okay, very simple. So Vd. So now I can rearrange it. A N L. Let us rearrange it. A N E. Let us take the Vd outside, and this is L cross B. Okay. L means length vector, unit length vector. Okay. This can be represented like this. So that implies now ANEVD. ANEVD. What is that expression? Can you remember that one? That expression is nothing but the expression of current. The expression of electric current, which we have discussed in the chapter number 3. Okay. So now here you can write edge. ANEVD is nothing but the ANEVD is nothing but the IE, current electricity. Okay, so that implies I can put the value of I here, electric current. So that is equal to L cross B. Okay, so now finally F M is nothing but I whole into L cross B. This is the expression of force. Listen very carefully. This is the expression of force. Okay, on a current carrying conductor which is present in a uniform magnetic field. Okay, so when a conductor having length L, area A is present in a uniform magnetic field B, then what is the amount of force applied on it? The amount of force applied on it, Fm is equal to I whole into L cross B. Okay, therefore that is equal to I L B sin theta. Understood all of you? And another question may be in your mind, sir, if I is equal to L cross B, then how we will, this is the magnitude part, that's okay. The last one is your magnitude part, but this is a vector form. So in this form, the F, the force is not only having some magnitude, but also having some direction. So how could you get the directions? This is a very important one. Okay. So the in this condition, in this case specifically, the force, the direction of the force can be found out using the Fleming's left hand rule. All of you look at it. Fleming's left hand rule. So what the Fleming's left hand rule states that, listen very carefully. The Fleming's left hand rule states that the three fingers, look at these three fingers. This is my forefinger, this is my middle finger, and this is my thumb. So I will stretch these three fingers in such a manner that the three are mutually perpendicular to each other. Okay. So now if I stretch the three fingers with mutually perpendicular to each other, then if the forefinger, listen very carefully, if the forefinger gives the direction of what? Gives the direction of magnetic field, the middle finger gives the direction of current, then the thumb will give the direction of the magnetic force. Clear all of you? So what the Fleming's left hand rule states that? Now it states that stretch your three fingers such as forefinger, middle finger and thumb in such a manner that they will mutually perpendicular to each other. Okay, in such a way that if the forefinger gives the direction of your magnetic field, the middle finger gives the direction of your current, then the thumb will give the direction of your magnetic force applied on this conductor. Understood all of you? Clear? So this is my Fleming's left hand rule. So in this, from Fleming's left hand rule, you can easily get the direction of this force. Understood? Okay. So this much for this session. So in this session we are discussing a very important part. Okay. From the exam point of view, this is important. So go through my video lecture very carefully. If you have any doubt, then you can contact with me or you can ask me the doubt. Okay, and I will solve it. Thank you so much. Have a good day.